All right. So today is the last day of our premium prep cohort, and pretty much the entire time today is going to be taken up with the technical interview. And the way that we're going to approach this is, challenge by challenge. It's going to be, just a series of breakouts after we talk about initially, what's on the technical interview. And, we've been talking about the technical interview this, kind of this whole time. And in, one sense or another, we've covered pretty much all of it, and including kind of showing something like an example at one point as well. Like after class, I think I showed you a potential mock interview that we have given in the past. Sorry, let me go ahead and reshare my screen. So with that said, let's kind of just dig into what is on the technical interview. Oops. Sorry, my drawing program loaded in the wrong window. 1 second. There we go. Okay. All right. So let's talk about just generally what's on the interview. So the TI is it's 45 minutes long. It's an hour long, but there's 45 minutes of coding time. And so you want to keep that in mind. It might be helpful for you to practice, say a series of problems that, with a timer, to get used to this idea that, okay, you're going to have this block of time, and you need to get everything coded in that time. What we're going to cover today, of course, we're going to stretch over the 2 hours of the class, so we won't really be, doing a mock interview in that sense. But I know a number of people benefit from doing mock interviews, and that is something that we can do for you. It's kind of first come, first serve, though, and we're going to be heading into our busy season really soon. Our team, and as you might know, our team curates, develops all the prep material, and we also conduct the interviews, and we also write curriculum for other teams, and we also, teach, say teach in the DSI or teach different workshops around. So our team gets pulled in a lot of different directions, and as such, mentoring ends up being available contingent on our bandwidth. So, if you want that mentoring, we're here to do it and we want to do it. The sooner you get into that pipeline, the better, right? And I just wanted to reiterate that point. I think I've mentioned that before. So you can reach out for a mock interview, and like I said, it's first come, first serve. And what else in this regard? Well, just generally, the interview is about writing Python. Primarily it's about Python. But the way we say it is, it's Python to explore statistical concepts. And with that in mind, what might you be reviewing, right? Like, what kinds of things would you review in terms of statistical concepts? Well, let's narrow that down a little bit. I would say review binomial, review Poisson. I'm going to put in parentheses geometric. The reason I'm putting this in parentheses is that we might ask you a geometric problem, but we're not going to, at this stage, give you an interview that's based in geometric. We have those in the works, but we don't have any that are, in production at the moment. And then make sure you clearly understand a uniform distribution and make sure you can make sure you do a couple Bayes theorem problems. I'm not going to say I'm going to say outright that we don't have we have conditional probability on, potentially on one of the interviews, but it's not going to be specifically Bayes' theorem. But if you understand Bayes' theorem, it'll be no problem. So this is, the aside from the basic stats concepts, which maybe let's call this, probability and distributions. Let's also think about, just stats. Understand mean. Understand, of course, understand median in that same vein. Understand variance, standard deviation. And anything else that we need you to understand in basic stats, you'll be able to construct from these. I think that's a fair thing to say. Okay, so this is sort of the core statistical concepts and probability concepts that we want you to know. And let me answer this question. By ask a geometric question, do we mean that it might just be a simple question where we find the answer and we aren't required to code a distribution function? Yeah, that's what I mean. Yeah, so it might be conceptual, how would you describe this, this procedure? And it might be something like, oh, well, the coefficients here look like a geometric distribution, something like that. But we're likely, if we ask you a question like that, it'll probably just be a thought question. In the type of question I would that you would really want to expect is, let's say you're flipping a fair coin. What is the probability you get heads on the third flip? And we wouldn't ask you to solve that probability necessarily. What we would ask is, what distribution represents this phenomenon? And that's what we would want you to recognize. That the geometric distribution can be used to represent that phenomenon. With any of these distributions or stats concepts, we'll give you the formula. We'll give you formulas. We're not going to expect you to have any of that memorized. So just keep that in mind. Okay, so that's in terms of the distributions and statistical functions. The other thing that you want to consider is sampling approaches. And the way that I've described these, I don't want to necessarily call these sampling approaches. Remember, we had kind of three strategies for exploring a stochastic or random process, right? Three strategies for a random process. One is counting. Two is sampling. And three is with some kind of closed formula, right? So just to remind you something about counting, let's say that, we're thinking coin flips again, and you're thinking about 4 coin flips in a row. It's going to be helpful to be able to count in that system, right? Tails, 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 heads, tails, tails, heads, tails, and so on. And the way that you do this is with, well, the way that if we were to ask you to do anything like this, it would be with, let's say nested for loops. That's the way that you might be able to figure it out offhand. That said, we are very unlikely to ask you to code a counting approach, but we do want you to understand a counting approach. With sampling, you're much more likely to write something that samples. You've got a few functions to think of, like you've got in the random package, you've got choice, you've got random, right? You've got these three functions. One that we used very quickly in passing was randint. There's a chance that you might see that. Just throwing it out there. If you do see it, all this does is gives you a random integer within some range, and we'll give you a little snippet of documentation on it. So that shouldn't be too hard to figure out. All right, so with the closed formula, right, we give you a PMF and you code it up. And that's, I think that's pretty you've seen that a lot so far. Okay. Oh, you know what? Apologies if my handwriting is not amazing, but so what else do you need to know how to do? Well, obviously code mathematical formulations. That's something that you will want to be able to do. What does that mean? What does that mean? Well, it might mean coding something like this. N, and let's say this is 0.7 I to the negative 1/2 let's say negative 1/2 I. Why not, right? So if you see something like this, right, like the clear implication of something like that is, well, that might take a for loop. And if we were to write this just offhand, write this in Python, we might say, oh, you know what? Let's put some data here. Let's say we've got some data that's like 9, 3, 7, 2, 4, and let's modify this math just a little bit to make it slightly more interesting. And we'll do times a sub, let's do a sub I. Okay. All right, so if we're looking at this, if we want to really think about what this is doing, we're going to say this is the first round of this is going to be 0.7 times 1 raised to the negative 1/2 times a sub I. A sub 1 in this case is 9. And remember, this is a mathematical representation, so we're indexing the mathematical representation at 1, Python would be indexed at 0. And so if we wanted to code this in Python, and obviously this is going to keep going, right, until we process all of the values in A. So if we want to write this in Python, I'm going to do one of those things that you have not seen me done, or you have not seen me do, where I'm going to just write code with a pen. And that's like just like a carryover from comp sci classes a long time ago, where they're like, here, you're going to take a test. Now code an entire program using pencil and paper. And we would never ask you to do that. But I'm just going to do this because it's fun. So we start some sum at 0, and we're going to make a for loop, and we're going to say for, let's say, index and num in enumerate, and I'm just going to say enumerate, just enum here. Let's enumerate A. So in this case, it's going to be sum will be incremented by what? It'll be 0.7 multiplied by the index raised to the negative 1/2, and then multiplied by num. So this might be something, the kind of thing you might need to do at some point. We'll do a problem that looks like this. This is a little intimidating. I just made up some numbers. But notice that the summation symbol here implies a for loop, right? This implies a for loop. And in this case, we've got the usage of the index, and it's valued at 1 to start, and we've got the usage of an item in a list, right? And the first item corresponds to index 1 in the mathematical representation, but in the Python representation, I'm sorry, we should start this enumeration at 1 over here. In the Python representation, we need to explicitly say that we're starting at 1, which I did not do, but I meant to do. So this is A, and then we start at 1. So we'll do a problem that looks more like this. You know, always remember, you can write code with a pen and paper, but you should never really do that because it doesn't make any sense. You can't run it or check your errors. Okay, so the one of the main things you're going to need to be able to do is manipulate dictionaries. Okay? We think of dictionaries as, you know, the most advanced base data type in Python that you're going to need to use on the TI. So what do you need to be able to do? Well, you need to be able to add values, right? You know, pack values into a dictionary. So I'll just say pack values. And there might be times where you need to check membership, right? Sometimes you need to see if a key exists in a dictionary in order to, you know, if you're counting a certain number of items, you need to check if the item's in there already before you increment the counter. So check membership in the dictionary, the key membership in the dictionary. And then there might be something where you need to transform a dictionary in some way. We did a lot of kind of toy problems around this where we took the probabilities from Poisson or binomial or something, and we transformed that dictionary from being a dictionary of counts into being a dictionary of probabilities, right? That's a thing you might do. Or, you know, you build a dictionary where the keys are some value and the values are a list of values, but then you sum that list of values and you take the mean of them. You know, that might be a thing that you would have to do. And then more generally, let's, you know, go back to this idea of the general analytic approach that we kind of set in motion throughout the course. You know, you create a generative process. And I want to say that the interview itself follows this sort of general outline, okay, this analytic approach. So you create a generative process. You sort of load a dictionary. And what that looks like in some sense is you are visualizing the data. You're, you know, looking at the data. You're putting it in a way, you're putting it in a structured form that you can kind of look at. And then ultimately, you know, you're kind of answering questions, right? And this is a very, you know, when I say answer questions, I also mean you're interpreting, right? You're utilizing that random process that you're analyzing. So, so in this answering questions or, you know, interpreting results, there might be a pattern that we want you to see. There might be a statistical concept that you're unlikely to have seen, or, you know, if you have a strong math background, maybe you have seen it. But you know, our goal there is to you know, have you experience some kind of epiphany around what we're doing. And in those cases, it's okay if you don't see the pattern, right? It's okay if you don't have that epiphany. We're going to talk with you through it and get a sense of your understanding of it, right? And that's, so either way that goes is fine. But that is part of the interpreting of the results of the phenomenon that you're coding. Okay, so are there any questions about the TI? If there are no questions, feel free to ask questions as we go through. But if there aren't any questions right now, that's totally fine, and we'll just jump right into. Sure, I can do that. I feel like there's a lot of slides on this. The main thing I wanted to point out was the 3 strategies, but I can also put this in here. Okay. All right, so let's look at some challenges. Okay, we'll start. We're going to start sort of. I don't want to say at the beginning, but let's. But it's sort of at the beginning. All right, so you're going to code the mean function, and I'll give you some data to work with. And yeah, let's put 4 minutes on the clock. Go ahead and code the mean function. Okay, so I'll just code through this very quick. Here's our toy data, and this is a mean function. I'm going to say, make this a little bigger. Say def mean, and we're going to pass in a list, right? So I'm going to pass in a list. There's an optional trim by parameter, so this trim by 0 by default, and then we can just say, here I'll make a copy of the list, and we can say if trim is greater than 0, then we will sort the list and we'll slice it to go from trim to negative trim. And we can just return the sum of that list and divide it by the length of the list. Okay, so I think that'll work. Let's call this, let's look at the mean of A. Oh, whoops. There we go. It looks like the mean is 238.3, which seems like maybe we want to trim something off, so let's just make sure that the trim is working. Let's trim 2 off on either side and see what happens. Looks like 26 if we trim 2 of these off, although this might be a problem where the mean isn't the most helpful metric for us to use. So I'm gonna, if you go back and you look at the slides for today, I'm gonna be skipping some of the challenges because I think some of the later challenges are more interesting. I'll skip the median function for now, and let's do the variance function. I think that is a good one to be able to code offhand. Let me see if I can get all of this on one page. Okay, so let's take 4 minutes on this one as well. So notice there's a population variance and a sample variance, right? So you're going to want to set a parameter for whether it's a sample. And notice we've got this summation symbol, so think about what that means. And notice we also have the mean, either represented as mu or x bar. So you'll want to code that into your function as well. So I'll put 4 minutes on the timer. Go ahead and code the variance function and make sure to have a parameter for whether it's a sample or population. All right, let's code up a variance function. Make this bigger again. Let's do right about that size. And variance, right? Spread of the data is a way we can think about the variance. Remember, it's sort of out of scale, because it is the square of the differences. And so we will pass in a list, and we'll make the assumption that it is a sample. If it is a sample, we're going to apply Bessel's correction, which means that we divide by one less than the magnitude of, or the number of items that we are considering. Okay, so we're going to get the mean, and I am going to start a total here, and we can say for each item in that list, the total is going to be incremented by the item minus the mean, and that is going to be squared, right? So that's a direct translation of the formula. And what I'm going to do here is I'm going to return the total divided by the length of the list. And one convenience here is sample as a Boolean. We can treat it as an integer, as the integer 1 or 0, right? So if we want to apply Bessel's correction, we don't actually need to use an if statement here. I can say it's the length of the list minus sample. If sample is true, then it'll be the length of the list minus 1. If sample is false, it'll be the length of the list minus 0. So let's get the variance of A really quick. And I will also paste this code into, the Slack presently. So let's just take a look at the sample variance. Notice that is massively out of scale, right, for what we are thinking this should be. And what would we do to bring that into a more interpretable space? Well, we could take the square root, right? We could just raise this to the power of 1/2, and 622, if we look at our original data, I think that makes decent sense. That's the average distance between each data point and the mean. The average squared difference between each data point and the mean. I think that makes sense looking at this. So let me go ahead and paste all of this in so far. And also notice that our variance function is dependent on our mean function, right? So that's something that you might have to do at various points, is write a function that is dependent on some other function. So be ready to do that. Okay. So let's move on from basic stats, and let's see what the next progression is. Yeah, let's code factorial. So we'll code factorial really quickly, or fairly quickly. I'll give you 2 minutes to code factorial. Starting when I start the timer, that is. And this is one of those ones that you should just be able to wing off the top of your head. So go ahead and code factorial. All right, there's a lot of factorials in there. I know we've coded this one a bunch, and pretty straightforward, right? So we establish a product, and we say for whatever, for num, in range we'll go from 1 up until n plus 1. We can't start at 0, we have to start at 1, and we can modify our product by the number, and we can return the product. So I think that that should work. I should always test my function just to make sure. So we'll say factorial of 5, which should be 120, and it is. Cool. And let me go ahead and put that in the Slack. And we'll just code a couple more mathematical functions that are dependent on factorial, right? So one of those is going to be the permutations function. So I'll give you that one to code. Oops. Let me just copy this, and we'll do a couple of these. So you're going to code permutations, and you're going to code combinations. And notice how closely those are related. And you could make combinations dependent on permutations. You also have the option of optimizing your permutations function, right? There's a way that you can do that if you recall how to do that, but it's not necessary. The sort of vanilla permutations and combinations are just fine. So let's do 4 minutes on this. Go ahead and code both of those up. All right, let's code these up. They're pretty straightforward. I'll code both versions that I usually think about for permutations, and then we'll just look at this. So permutations, and this is n permute k. We can return the factorial of n divided by the factorial of n minus k. I like to cast that to an integer. I think it's better, or it's more, indicative of what factorial is. And then let's look at another version of permutations, and that'll just be the slightly optimized one where we take permutations and permute k, and remember we can sort of construct this like factorial, and then we're going to go from n, and we're going to go down to n minus k by -1. In the negative direction. So if it's 5 permute 4, then we'd start at 5, and we'd go down to 1, and we'd go in reverse, right? So that's all that is. And then we can say permutation. This is sort of the same construct as factorial, and then we can just return the permutation. This is just slightly better in terms of performance, but for our purposes generally, either is totally fine. So with combinations, we can just say, with n choose k, we can say return. Well, we can do this a couple ways. We could return the permutations multiplied by 1 over factorial of k. That's one way we could do it. But we could also just do the formula explicitly. So I'll just do that, and this will be multiplied by the factorial of k. The more optimal version of this would simply be taking this factorial of k, taking this permutations version up here, and just dividing perm by factorial of k. So I won't redo that here, but just so you know that that's what's going on there. All right, so let me copy all of these. Should probably test them, which I'll just do really quick. So let's say 5 permute 5, and then let's say combinations of 5 choose 5. What should that be? What should the combinations of 5 choose 5 be? Turns out that is 1. Wait, permutations 5 permute 5. That should not be 1. Huh. What's going on there? Does anybody see my error? Line 43 and line 40. Oh, it's right here. I was doing times gets 1, and it should be times gets I. Yep, there we go. 5 factorial is 120. 5 permute 5 is 120 because it's just 5 factorial. And then with combinations, it's just, there's only one combination where you use all the items. So let's change this to 5 choose 3. And that makes more, we see more combinations for 5 choose 3, and then of course we would for 5 choose 5, because there's only one way to have all 5 items, and that is what 5 choose 5 represents. Okay, so let me paste these in. Okay. All right, so the question is, I'll answer this other question first. Why do I prefer the iterative version of factorial instead of the recursive version? In general, I will code something in the iterative version and avoid recursion. in most cases. And my reasoning behind that is it is much more readable, and I think recursion can give you very elegant code that's hard for people to understand. And if there is an iterative version, how do I say this? If there is a tenable iterative version of an algorithm, I'll tend to use that. Like when I coded out heaps, I coded an iterative version of heaps instead of the recursive version of heaps. And I think that's coming from, a C background and, thinking low-level programming and thinking in, how to best communicate in code with people. I'm not totally averse to recursion. I think it's great, but I tend to not use it unless it is really elegant. Okay, so what syntax is giving the I equals 1 to n for the capital sigma summation in my version of the Python code? Sure. So let's think of, this will just be a brief aside. Let's think of a problem, a fairly simple problem. Let's do, we have our list A, and let's do this. Let's do 2, 4, 6, 8, 10, 12, and not move the canvas around. And let's make some summation where we say I starts at 1. The first item is how we want to think about that, and we'll go up to n, and we'll say a sub I multiplied by 1/4 to the I. And we'll just take a look at what this might look like in the processing of A. So there we go. Oh, I actually just want to be able to see this, don't I? So I'll just do something like that. Okay. So let's just put A in here first. This is just 2, 4, 6, 8, 10, 12. And normally I would, well, I guess right now I am normally doing this. So I'll do that. And let's make just a simple function called proc list for processing this list. We'll pass in a list. And what we're going to return is some summation, and thinking about this from the mathematical representation translating to the Python representation, what we might say is for index and number in enumerate, and we're going to enumerate that list, and we want to start it at 1. And the reason we want to start it at 1 is that I is 1 in the mathematical representation, so we're saying A sub 1. Well, A sub 1 actually corresponds to the first item, not the second item, in this mathematical representation. And then when we multiply this, we'll multiply it by 1/4 to the I. So let's say sum is going to get incremented by the number, right, multiplied by 1/4 raised to the index. And then we can return the sum. All right. So if we call this, right? Oh, whoops. Yep, that's it. If we call this, we can take a look at what this looks like. Okay. So that processes out to 0.887. I think this actually becomes much more interesting if we get a list of numbers. So let's do get list, and we'll pass in a number of items. We'll do 8 numbers by default, and we'll take choices from this list. So we'll do 1, 2, 3, or 4. Actually, let's do 0, 1, 2, or 3. I think maybe that'll be interesting. And we'll just, for whatever in range n, this is a place where I would probably use a comprehension. I think it would be just one line of code would be nice. We're going to get some numbers. I'll say out.append a choice from 4s, and then we can return 4s. Of course, if I do this, I'm going to need to say from random import choice. And I think this will give us some numbers we can look at. Okay, so 0.737, 0.737. Okay, well, why is that happening? Because I am not calling this on getList, which I should do. So maybe I'll do this. So I'll just get the list out first, and we'll leave it with the default. And then let's print the list and the number generated by that list. Actually, let's do it in the other order. Do that. So we have some random process here, and we're modifying that through this function. And we're going to look at the relationship between the list that's generated. Oh. What is happening? That just seems so unlikely. Okay. What am I doing? I'm returning 4s. That's what's going on. All right. That's easy. Okay. So now we have something a little bit, a little bit more meaningful. We can look at a number that's generated, and we can, tie that to, let's say, tie that to a process underneath it, right? So we generate this this value. If we get all 3s, we can imagine what that number will give us. If we get all 0s, of course, we're going to get 0, right? So this might be an interesting thing to look at. We might consider, what is this actual distribution? What is this distribution of numbers? I have a suspicion, but I'll leave that for y'all to play around with if you want to. So, there we go. What's the recursive version of Factorial? Let's look at that at the end of class. If you're interested, it's really elegant. It's a couple lines, but it's also, how do I say this? I never want to bash recursion, but I also, I think if you're writing very simple code, recursion is fine, and I'll say it like that. And yeah, we can look at it in a little bit. Oh, actually, let's take a break right now, since we're at the hour. Let's take 6 minutes, and when we get back, we're going to jump into distributions, and we'll just plow through a lot of those, and then we'll look at some other kinds of random process problems. Okay, so I'll see y'all back here in about 6 minutes. All right, so I answered a question, and I think I answered not the question that was being asked, but a question that I assumed was being asked. If you can clarify the question, that would be helpful for me. I think what I can do is just walk through variance really quick, and we can think about it this way. So let's talk variance, and I'll just write down the equation and talk through it while you're posing your question. So we've got sigma squared. This is the population variance, so we're saying 1 over n is going to be the sum of the squared differences between each data point and the mean. And so this is going to be the sum of the squared differences, right? So this is each data point in some data set X, right? So maybe this is 2, 4, 6, 8, 10, something like that. And the mean, which is just the mu that has been calculated. Now, sigma squared is the population variance, right? And we have our sample variance, which is essentially the same equation, except we apply Bessel's correction, where we reduce n, the division by n, by 1. And so what this looks like is s squared. Notice we're not calling this sigma anymore. We're saying 1 over n minus 1. Pretty much everything else is the same. We're going to go from I equals 1 up to n. And this time we're going to represent the mean with x bar instead. So we perform this chunk of the operation, and we keep accumulating from it. And that's how the for loop sits in there. So is that... let me see if... what syntax is giving the I is 1 to n for the capital sigma summation in the Python code. See, the nice thing about that is we can just iterate over the items in the list. We don't actually need this value I, right? We just need each item. So it's just a basic for loop. It's just for num in X, right? For num in list. Okay, yeah, that makes a lot more sense, because we don't need, since we don't need the index, we don't need to enumerate. We don't need that index at all. So we just use for item in list, however we frame that. And there was a question about factorial. I'll just show you. I actually updated this in the slides. I put a quick recursive factorial in there. So why don't we just look at the recursive factorial really quick, just for fun. Oh, did I save this document? I hope I did. Okay, I did. Good. All right, so the way that I wrote this, just really quick, if we're taking the factorial of n, we can, the first thing we want to do is check for our base case, which is going to be 1. And what does that mean? It means that when we get n down to 1, then we can return n. So this is, in essence, if we pass in 1, we know the factorial of 1 is 1. And that is a starting point. And then in all other instances, we can return n multiplied by the factorial of the recursive, the factorial recursive of n minus 1. And if we want to see kind of what this looks like as we go, what we can do is print n. I think that should give us a good sense of it. Let's take a look. So let's print the recursive factorial of 5. Or let's do 9, just to have a few more cycles of this. And I might make this a little bit different so that we can better see what's happening under the hood. Oh, well, that makes sense. Let's print this and see how this is growing. So let's print n, and then let's print that. Okay. And oh wow, that is not very easy to read. What is a good way to make this really explicit what's happening? I mean, I think this is the thing, like, I mean, recursion's great, and it's also trying to figure out a good way to describe what's happening here is not great. So let's just print the factorial of the recursive value for n minus 1. I mean, the thing is, like, even printing this value sort of is invoking recursion, so it ends up being even messier. But this is working code. I mean, you know. So I don't want to take up too much time with it, but I'll throw this in the Slack. Okay. Yeah, we can have recursion some other time. Let's see. Okay, great. Let's continue into, let's start in on distributions, and we'll see how far we get into the distribution. So the first, kind of the root of it all is the Bernoulli function, right? So I'll have you code a quick Bernoulli function. Remember, Bernoulli is just going to return, let's say, a 1 or a 0. 1 indicates success. If, if that, how about we say this? If you put in a probability of success of 0.5, then there should be a 50-50 chance that you get a 1, right? You should get a 1 50% of the times. You should get a 0 the other 50% of the times. If you put in 30%, if you put in 0.3, that is, then you should only get a 1.3, 30% of the time, and you should get a 0 70% of the time. So if there's any confusion about how to do that, we'll just make that clear when we solve it. Okay, so let's look at a Bernoulli function. Probability of success, I'll default that to 0.5, why not? Thinking about a coin flip, I'm going to take a draw. So I'll get a random number between 0 and 1, which means that I need to import the random function. And next I'm going to say if the draw is less than the probability of success, then we should return 1, and otherwise we can return 0. So let's just make sure that works. That's going to be Bernoulli of, I don't know, let's do 0.3. Right, so if I run this a number of times, it should take a little while before we get a 1. And we should get this at a frequency that represents, if we do this a whole bunch of times, 30% of the values we should get should be 1, and 70% of them should be 0. So there is that. And oh, my apologies. I thought I pasted variance in, but maybe I didn't. So here you go. I'm going to paste variance in again. Okay. All right. Let's go from there. Let's think about some other, other things that we've talked about in our distributions. Let's sort of, here's a good one. I think this is always a good one to do. Write a function called getListOfBits. The get in here, just in general, we shouldn't name our function starting with get. I should fix that in the slide, but it's fine for now. So this should take one argument, the number of bits, and it should return a list containing random 1s and 0s. So go ahead and code up that. All right, let's code this. This is a pretty straightforward function to write. I think I am just gonna name it list of bits just to try to hold myself accountable. There'll be a number of bits there, and we can say return let's say random dot, sorry, it's just choice between 0 and 1 for whatever in range number of bits, and that should give us, so I'm using a comprehension here, but you know, broken out, this would look like, let me write it broken out. This would be, you know, so we have some bit list, and we're going to say for whatever in range, and it'll be just the range n bits, and we can say that bit list will have appended to it a 0 or 1 throughout that process, so we can return the bit list as such. And I think either of these should be fine. You know, we're not asking you to write comprehensions at this point, but I do think that they are a good idea before very long, because they're nice. Oh, generator has no length. Where is that for whatever in range number of bits? Choice. Oh, I see. I'm missing a closed parenthesis. There we go. I think that's it. And I have an error there as well. All right. Yeah, and there we get some random bits. So those both look like they should be fine. Right, and this is just two different ways of writing the same function, so not a big deal. Ah, okay. Yeah, I think that makes sense. In the sigma notation, what gives I and what gives n? Yes, I can answer that. I think that's a good question to answer. So I is going to be the position of an item in a numeric list or in a list of items, right? So this first item has an I of 1, right? The second item has an I of 2, third of 3, fourth of 4, fifth of 5. This is in the mathematical representation, right? And n is how many items there are. So if we start at I equals 1 here, we're going to start with 2, and we're going to insert 2 in for this x sub I, and then we're going to subtract x bar from that, right? And, you know, we're, of course, going to square that and so on. And then we add to that, you know, 4 minus x bar squared, and so on, up until the last item, 10. So all this I equals 1 to n means here, in this case, is every item in this collection x. That's all that means. So if I'm understanding the question accurately, the I is 1 is just indicating the index, and n is indicating the length of the collection. What gives I and n in the sigma notation in the Python code? Well, we don't need I or n. It's implicit in this construct of the for loop. So maybe I'm misunderstanding the question in that sense. we don't have an I or N in this sense. What we could do is we could make an I, right? So we could say for I in range, the length of the list. We could write this in a different way so that we explicitly have I. And this is going to be I from the range from 0 in this case, up to the length of the list. And then our total is going to be incremented in relation to this list. So it'll be list sub I minus the mean squared. So that would be a different version of the variance function where we have an explicit I, right? So this is sort of like, here, the summation is represented here, right? This is the, the construct that gives us the, essentially the sigma notation, the summation. And then this is what's to the right of the summation. And here's our I starts at 1, except here it's because Python is 0 indexed, we start at 0, up until n, which is n is representative of the length of the list. Well, we're not, so you have to, the way to think about I in this case is it is an indicator of the index that we are referring to. And in Python, the first item is 0 indexed. In the mathematical representation, the first item is 1 indexed. This is actually a confusion that comes up a lot. I try to, point this out. I try to point this out like kind of throughout these materials. In the mathematical representations, we'll say, well, this is 1 indexed because it's a mathematical representation. That's generally going to be the case. Although sometimes you'll use 0 indexing in mathematical representations, but generally you'll use 1 indexing. And Python is 0 indexed. So maybe that explains some of that discrepancy. And let's look at, we're going to construct a binomial process. So let's look at this. I think this is getting into the realm of the types of problems you might see on the technical interview. I think this is a good example. So you're going to write a function called binary sampling dictionary, and it's going to have 2 parameters: the number of the bits for a randomly generated list of binary, and I'm realizing maybe I did not paste in my code. Is that correct? No, I pasted it in. So you're going to need the list of bits function to write this. And you're going to return a dictionary, right? You're going to return a dictionary that has this structure. So let me just kind of fit this in here. Where, let's say 0 bits occurs 35 times, 1 bit occurs 63 times, and the keys here are the number of successes, and the values are the counts of that number of successes occurring in num samples times. So this is getting into that realm of the kind of problem you're going to see on the TI. And so, definitely pay attention to this problem and think of it as the kind of problem that you're going to want to generally be able to solve without too much trouble. So let's do a timer of, what should we do on this? Let's do 5 minutes on this. Okay, go for it. All right, so let's code this. Our function is going to be called binary sampling dictionary, and it is going to rely on this list of bits function. So we'll call this binary sampling dictionary. There are two parameters. Number of bits is 8. Number of samples by default is 1000. Okay, so how do we want to think about this? One of the things that we're going to think about is the establishment of a dictionary, right? We're going to collect everything into this. All right, so we have this dictionary, and we're going to then perform sampling num samples times, and this is where we get into this for whatever in range num samples. And from there, we're going to call out to list of bits. And what I'll do here is fairly simple. We'll just say, we'll call this the bit sum. It is going to get the sum of the list of bits of n bits, but actually this should be num bits. And at this point, we want to check for membership of that bit sum in the dictionary. So let's say if bit sum is not already in the dictionary, then we can put it in there. We can say d sub bit sum is going to be set to 0 by default. And oops, I need a colon there. Then after I do that, we can just increment it by 1, and that is it. We can return that dictionary. So this is going to give us sort of an estimated binomial dictionary, right? And let's think about this for, well, let's just traverse it. So we'll say for key value, I'll say count for key k and count in binary sampling dictionary, and we'll just use defaults dot items. We can print, in this case, we're going to want to sort this, right? Because we don't know what the first value is going to be, right? It won't be in order, or it's very unlikely that it will be in order. And then we can print the key and the count, and we should see a counts, an estimation of counts for a binomial process. Okay. So let me just expand that a little bit. Okay. And there it is. So we can take a look at this. This is output in a slightly nice way. I think this is something that we can essentially see. This looks binomial-like. Cool. So let me paste in this, and then I will paste in the other, some other code. So I think there was a request for this sketch, so I'll paste this in. And I modify the variance function, so I can paste that in as well. So I'll just put these directly in. Okay. And where did I do variance? Right there. Okay. Yeah. So this is one. This is the one where it's just explicitly showing Python being 0 indexed and giving a sort of an indication of summation happening. Okay. All right, so let's see, we've got about 15 minutes. I want to be a little bit selective about our next problems. That was a sampling approach. I think I want to skip these other binomial problems, and let's look at the Poisson PMF function, and then we'll probably wrap up with the Poisson PMF dictionary. So let's take 4 minutes on this one. All right, there's going to be an import on this as well. So go ahead and code up the Poisson PMF. You can hard code E. I recommend importing E. Okay, so let's look at this really quick. I really like the question in the Slack about how to do a random sampling from a Poisson distribution, right? And it's an interesting problem. So one way that you could go about it is you could use the Poisson PMF to generate a list of probabilities, a dictionary of probabilities, and then you could utilize a Bernoulli function, right, to get a value in the range between 0 and 1, and you could well, essentially have a Poisson CDF and then range that out. So you look up a value in you look up a value that has a probability closest to that Bernoulli probability, and you could sample a Poisson process doing that. It's a bit cumbersome. It's a little bit like a closed loop, you could say, but you could totally do it. Sorry, that's a bit of an aside. I just thought it was a really fun question. So I'm going to import from math. I'm going to import E. We already have a factorial function, so I'll just leave that as it is. And I'll say, for this Poisson PMF, we can pass in a lambda and a k, and we are going to return lambda multiplied by, lambda to the k, multiplied by e to the negative lambda. I usually write this in the other direction, but it doesn't matter. It'll be the same function, divided by the factorial of k. And there are a couple values I know offhand. I always just want to test my functions, and we print 10 and 10 for these, which should be something like 0.125. And it is. Okay. So that's pretty straightforward. The next step of this, and we have just enough time to do this, is coding a Poisson. Well, we could code a Poisson CDF function, but let's not do that. Instead, let's code a Poisson PMF dictionary. I think that's more in line with what you're likely to see. Well, I say that, and I think you are likely to code a CDF function for Poisson, but depending on which interview you get. But there's this whole technical interview review sheet, right? The slides from today, we're skipping around a little bit, but this is here, and it's a good practice document. There are a lot of good practice documents, and this is one of them. So feel free to revisit it. I'll put 5 minutes for this, and that'll give us just enough time for me to code the solution when we get down to time. Okay, I'm going to code this up really quick. I'm liking this line of thought on setting up a sampling process for a Poisson distribution. It's an interesting problem, and it's doable. You know, it's something if you put a little more thought into it. I mentioned Bernoulli. I didn't actually mean to mention Bernoulli. I think that was you just want to get a random number between 0 and 1. Okay, so the Poisson dictionary, PMF dictionary, that is. So the Poisson PMF dictionary, we're going to pass in a lambda, a low k, and a high k. I probably want to put def in front of that. And we establish a dictionary. And we say for k in range, we go from low k to high k plus 1. And we can just say d sub k is going to be the Poisson PMF of lambda and k, and then we can return d. So that's it, really. If I call this, and I'll call this with a lambda of 10, lambda of 10, a low k of 0, and a high k of do 20. And then we can traverse this for k, b, and d.items. Keep in mind you don't need to sort this because it's going to be in order. It doesn't hurt it to sort it, but it won't affect it. And yeah, and then we can just add in that value. Might as well round the value, and I'll round it to 6 decimal places. Okay, and if I run this, that looks like a Poisson distribution. Now, can I code in 1 minute a Poisson CDF dictionary based on this? Let's just see. So let's say we have a CDF dictionary. We have a proba range. Let's just call that a proba, and we'll start that at 0, and we'll say proba gets that Poisson PMF, and then we can just increment this by, oh, whoops, we just put proba in here. Is that right? No, sorry, I need to increment proba, and I think if we run that, we should see a CDF dictionary. So I can use that to frame this idea that I'm having. Oh, that did not work. What is going on there? Thought that should work. Oh, that's because I'm calling the wrong function. Now that should work. Yeah, okay, perfect. So that is a CDF version of that. All I'm doing is establishing an accumulator of those PMFs as we go, and so that gives us a cumulative distribution function where we continually add in the new probability. Okay, so I'll paste those in, and I'll throw that in there. Cool. So this is the last class. If you want to transfer into the upcoming Premium Prep cohort that's starting on Tuesday, definitely feel free. I put the link to transfer in a couple places. I sent an email, to fill out the post Premium Prep survey. Please fill that out. Please give us feedback. We're constantly iterating on this, and we take all suggestions into heart. We can't change everything the way that we would like to because of certain constraints, but we definitely appreciate all feedback. And set up mentoring. We're still fairly available for the next couple weeks for mentoring. Keep coming to study halls. Do everything. Practice. Like, really, that's what a lot of this comes down to. Practice these materials. Practice on Code Wars, especially the 8s and 7s, level 8s and 7s. Those will just give you your legs in Python, right? Those repetitions, they make a huge difference. They really do. And you don't have to worry about writing perfect code. You don't need to understand every concept, but you do need to have that core set of competencies that we're asking for. In your review for the TI, probably the most helpful lectures are going to be in regards to statistical counting, obviously binomial and Poisson, and the continuous distributions as well, but focusing on the code for the uniform distribution. That's probably the most helpful set of things. Yeah, and if you have questions, always reach out. We're around a lot, and our main priority is working with you all to get you there. So yeah, definitely do that. It's been a pleasure. Thanks so much. I'm going to see a lot of you in the next round, and yeah, just keep studying and keep it up. You all are doing really great. So I'm going to go ahead and stop recording, and we can